right, so for our science panel, our very first speaker, they're going to be giving lightning talks, and then we're going to do a Q&A discussion. I'm going to invite up Dr. Edward Castaneda, a wetland ecologist with the Division of Environmental Resource Management for the county.
Good morning, everyone. It's a pleasure to be here. So I'm going to give you a quick overview of drivers of change in mangrove wetlands in the Florida coastal Everglades. Before I start, I have to acknowledge our funding sources, the National Science Foundation, through the Florida Coastal Everglades LTR program. Mangroves in the Florida coastal Everglades are located within Everglades National Park, and they are unique ecosystems in the sense that it's a karstic oligotrophic phosphorus systems where phosphorus is supplied by the Gulf of Mexico instead of the upper watershed. So mangrove forests are the dominant feature in the coastal zone. They basically represent the largest distribution of mangroves in the continental US and also a large reservoir of carbon across the coastal landscape. So in the Everglades, we have a distinct landscape vegetation patterns that is basically a function of environmental gradients, including resources, regulators, and hydroperiod. And these gradients interact also with hurricanes disturbance, defining different productivity and structure patterns that is resembled in different mangrove ecotypes across the coastal landscape. For instance, this is one example of the distribution of above ground biomass in Everglades National Park. So we had the largest and more developed mangroves in the western region, particularly in the Charles River estuary. And also we had less developed mangroves in an stunted form in the eastern region, including Florida Bay. So besides this, we know that South Florida is characterized by a high recurrency of tropical storms and hurricanes. And these storms, they really create significant effects to the mangrove community. So 19 storms had impacted the FC since 1928. And in the last 18 years, two hurricanes, Wilma and Irma, they have created significant damage and changes the ecological properties of mangrove forests. So one example is using our long-term data on primary productivity of mangroves in the Charles River estuary. What we observed basically is it was a significant decrease in productivity between 50 and 70% as a result of the massive defoliation. However, these mangroves are highly resilient, and what we observed is that rapid recovery within 5 years. So this is significant to assess or estimate the resilient capacity of these mangrove ecosystems. In addition, we know that sea level rise is a main press here in the Everglades. And then recent studies that we have are basically assessing that the accelerating rate that we have of sea level rise relative to historical changes are basically modulate the mangrove extent. And what we see is we have observed a significant increase and transgression of mangroves into the coastal zone in the southeast Saline Everglades. Also, we see that by 2009, the mangroves completely colonized the freshwater marshes. So understanding patterns of mangrove ecology, including resources and regulators, is important to assess an interaction with climate change variability, sea level rise, and hurricane disturbance, because it's going to give you a clear understanding of the patterns of distribution and carbon budgets of ecosystems in South Florida. Thank you.
All right, next up, I have Dr. Jim Forkran, Distinguished University Professor. Oh, he has fans. Distinguished University Professor of Biological Sciences and Director of the Coastlines and Oceans Division of the Institute of Environment at Florida International University.
All right, thank you. So this is definitely a lightning talk. I was told 3 slides, 3 minutes. Hopefully I can hold to some of that. So I'm going to talk about Biscayne Bay seagrasses and talk about the history of seagrasses. And my take-home message is, don't believe that the Southern Bay is a paradise. There are problems in the Southern Bay. So beginning in about 1925, we really started changing seagrass distribution, not primarily back then by water quality, but by dredging and filling and creating islands and changing the whole distribution of the bay. But we have a lot of data that's been collected over the years that shows us how we've really changed the system. So between that left one is 1925 and the right one is 1976. There was quite a bit of loss of seagrasses, especially from the southern part of the area around what became the Port of Miami. And then we knew by 1983, with the first real comprehensive mapping of seagrasses were done in the bay, there was quite a bit up in the northern part of the bay, and southern bay were nice, beautiful seagrass meadows. And in the mid-1980s, we really started to see a very rapid recession of seagrasses in the northern part of the bay, up there where the phosphorus concentrations are going up the fastest. And if you track those lines from blue to red, those are successive years tracking the loss of seagrasses over 1985 to 2016. So this is what prompted really that first Biscayne Bay Marine Health Summit. So we know what's going on there. It's classic nutrient pollution. Phosphorus makes fast-growing things outcompete the seagrasses, and the seagrasses die from sulfur toxicity. Talk more about that if you would like. But the rest of the bay is also seeing early signs of the same sickness. These are 4 time series plots of derm data that they've been collecting routinely since 1999. And what I want you to see is they go from very green in 1999 to 2004 period to not nearly so green in 2015 to 2019. So there is a long-term loss of seagrass abundance in the southern part of the bay, and that is coupled with a long-term increase in algal abundance. And these are not microalgae, these aren't the harmful algal blooms in the water column, these are algal blooms across the bottom. So we're seeing these, and why? Laura Reynolds has a poster out in the lobby if you want to see these pictures up close. Why? Phosphorus. We're loading the system with phosphorus, and when we do that, we make it so fast-growing things outcompete slow-growing things. And we love our slow-growing seagrasses and our slow-growing corals, and we don't like our fast-growing harmful algal blooms. We know the whole system is phosphorus limited. You add phosphorus, you change the system, you make it less valuable to us here in South Florida. Thank you.
All right, thank you so much, Dr. Forker. Next up, I have Dr. Natalia Quinete, Assistant Professor at Florida International University.
Thank you so much for the introduction. Actually, what I'm going to be talking a little bit more about other type of contaminants besides the traditional phosphorus and nitrogen that we have been hearing here. It's just like a very short talk, about 3 minutes, but a little bit of what we have been doing in my lab on emerging contaminants, more specifically on PFAS, an overview what we have been found in the bay. So what are PFAS? I think like maybe some of you have already heard about it, also known as forever chemicals. They look like something like the structure that you see over there. So long carbon fluoride chains. They have been made for a long time, used in a very wide range of household products, commercial application. You can see some in these pictures, like non-stick cookware, we have it in food packaging, firefighting foams, and so on. They preferentially bind to proteins. So that means that they actually being found in human blood. So 99% of the population actually being contaminated with PFAS. They have been shown to have a couple of adverse effects. I'm just mentioning some of them, like they have been causing certain types of cancers, affect the reproduction system, as well as affecting the thyroid and immune system. So here we started over looking at some of the canals. I think like everybody was already mentioned here, some of the canals that's discharging to the bay. So what we found out is that especially like, some of the canals like Little River, Biscayne Canal, and you see Seaboard Canal here that is discharging to Miami River that goes into the bay. These are the ones that show like the highest concentration of PFAS. So this is the sum of PFAS. So we have been detecting along like 30 to 40 PFAS in the bay. And here we saw like some of the most common ones like PFOS, BFHXA. So those PFAS, I mean, they're using like a wide variety of things that I already mentioned before, like in consumer products. So what we found out is like, especially like we look at some different transects all along the bay, And we saw that the highest concentration, as you can see here, is closer to this canal. So, and then because of dilution, actually this concentration decreased and was going to the offshore areas. And we also sample surface water as well as bottled water. And we saw that the highest concentrations were also in the surface compared to the bottle. So, and again, I think like besides we also found in the south area, but we can see that the north area section from the bay was the one that has actually higher concentration compared to the south. And I mean, you might be asking like, where it is coming from? I think we already heard about it, but you know, like we have those compounds like, you know, coming from wastewater leaks, failing septic tanks. They can be coming out from landfill leachate, urban runoffs, like from airports, military air bases, especially when they use like these firefighting foams. So, and then what we did also, we did like this forecast, so kind of predicting it, how it would behave based on the concentrations that, I mean, based on the points that we collect in the bay. As you can see here, red means like, you know, the highest levels of PFAS were found, and then the green is the lowest one. So you can see that the concentrations were coming in from the closer to the canals and decreasing as it goes offshore. So it's very. And I just wanted to acknowledge all these amazing people, you know, my students and postdoc. Without them, like, you know, this work would not be possible, and NSF CREST funding. Thank you.
All right, next up, I have Dr. Diego Learman, Associate Professor at the University of Miami's Rosenstiel School.
Thank you. Thank you for the invitation, Julia. So I'm presenting on behalf of the IBEAM program, that it's Integrated Biscayne Bay Ecological Assessment and Monitoring. In one form or another, this program has been going on in Biscayne Bay for about 25 years. It is kind of bittersweet for me. It's heartwarming to see how many people in this room, how many people care about Biscayne Bay, but it's also heartbreaking that Biscayne Bay last week lost a true champion with the passing of Dr. Joan Browder. Most of you have probably known Joan in one capacity or another. She was the founder, one of the co-founders of the IBEAM program, and a esteemed colleague for about 30 years. But IBEAM combines 4 efforts focused on the nearshore environments of Biscayne Bay between Matheson Hammock and Turkey Point. Why that area? Because that's the area that's going to be impacted by SERP, by the Everglades restoration programs. So we focused our attention on these nearshore marginal environments as canaries to the whole bay. The 4 components of the program are water quality, focusing on salinity. You will hear a lot about nutrients over the next few hours, but please don't forget about salinity as a key driver of the abundance and health of benthic ecosystems and associated taxa. That's run by Hervé Jobert out of Biscayne National Park. We have the SAV component run by my lab and Martina D'Alessandro. We have the mangrove fish component run by Joe Serafi and Evan D'Alessandro. And finally, the epifaunal component run historically by Joan Browder. And again, we're focusing on the area where the SERP impacts would be felt the most. We're focusing on salinity as the key driver of the abundance distribution and condition of the both the benthos and the associated organisms. And we've come up with different metrics to quantify salinity patterns with the keeping in mind that the target for the nearshore environment of Biscayne Bay is to recover and maintain mesohaline conditions. So you can see all of these metrics put together and note that over the past 30 years of doing this work, we realized that the mesohaline conditions have not been reached, or if they have, they don't persist. So this is still on the to-do list for SERP for this area. When we're looking at the seagrass cover, this is about 15 years worth of data. This extends a little further back. I started doing this work in 2003, so I have 20 years worth of data. And again, you're going to hear a lot about declines all around Biscayne Bay in terms of seagrass abundance and distribution. This is probably one of the examples of persistence in these environments. So the top line is the combined cover of all seagrass species. And you can see that it's gone up and down, but pretty much it stayed stable over the past 2 decades, which is really good news for what is a very marginal dynamic environment. So you may say, well, maybe seagrasses have stayed that way because they haven't experienced any major disturbances. Well, if we know anything about Miami or Biscayne Bay is that, it's never boring. So we've gone through hurricanes, we've gone through hypersalinity events, algal blooms, and more recently, sargassum impacts, and seagrasses have persisted pretty much the same cover over the past 20 years. Again, good news in that regards. This doesn't discount any of the other large mortality events, but in this area of the bay, we're seeing persistence. And we're also seeing some good news in terms of the shift in community composition. Again, the targets for SERP for these areas are an increase in the mesohaline frequency, but also more diverse seagrass community, reducing the overdominance of Thalassia and increasing the contribution of the other species, specifically Haliduli. And we can see that over the past 5 years. Now we have a bit more of a diverse mixed community in these environments. Quickly going on to the epifauna and the mangrove fish, the outcomes of our work show that the patterns are very species specific. We've seen stability for the pinfish, we've seen slight declines for the shrimp, and we've seen increases in the abundance of gray snapper. Again, depending on how different species react or respond to salinity, we're seeing their trends either stabilize or slightly increase or decrease. But the cool thing about our research, our historical research, is that we now have really robust statistical models that we can use to predict the outcome of SERP scenarios and what the associated fauna will do when the seagrasses change in space and time. And I'm going to leave it at that.
Okay, last but certainly not least, I'd like to invite up Dr. Catherine McDonald, University of Miami Research Assistant Professor and Director of the Shark Research and Conservation Program. Thank you, Catherine.
Thank you. Some of my students are here. I heard that. So I'm going to try hard to stick to 3 minutes, but I have a lot more than 3 minutes of things to say about sharks in Biscayne Bay. So please come find me if you're interested in hearing about them at length. So when we talk about conservation, one of the things that we're often talking about is the identification and protection of essential habitats. And our work and data shows that Biscayne Bay is likely an essential habitat for many of the species of shark that live here. That includes it being a nursery, gestation, mating, or pupping habitat for at least 10 species of sharks. If we include their relatives rays, we're probably up to closer to 13. That includes several critically endangered species, including the great hammerhead, and some species that are highly migratory as adults, also including the great hammerhead, and that are therefore really difficult to protect and conserve once they leave nursery habitats. That makes identifying and conserving those habitats even more important. Shark nurseries generally are threatened globally. They're threatened by a lot of things, and here in Miami, they're threatened by pretty much all their threats at the same time. Climate change, coastal development, including the effects of poor water quality and habitat loss. Many juvenile sharks are mangrove associated or shallow seagrass bed associated, so we can imagine that Biscayne Bay habitats are really important to them. We see reductions in prey species that make it harder for small sharks to survive. Pollution, both nutrient pollution and obviously the more direct effects of like actually running into trash and getting stuck. And the effects of this are really species specific, right? Some animals are pretty hardy as juveniles, others are much less so. Some are more able to move if conditions change in a way that's unfavorable for them, others less so. We tend to think about nursery habitats as looking more like the top, but increasingly our evidence is showing that they can also look like the bottom. Many species of shark are still using Biscayne Bay for these important life history events. And that means that we have a chance to make sure that they can do that into the future. But our data suggests that we may be approaching some tipping points. Currently, The Shark Research and Conservation Program is working on a lot of different topics, but they include studies of pupping and growth rates in these nursery habitats, studies of juvenile habitat use and feeding ecology. If you're interested in the feeding ecology of juvenile great hammerheads, my PhD student, John Flavin, will be talking, I think, at about 4:30 now. Mating and gestation. If you're interested in the gestation process in Biscayne Bay, my student Katie Miller has a poster over by the Johnson Center's table that I would encourage you to go check out. I'm particularly worried about climate effects on nurseries. I think that our juvenile sharks could be resilient to changing temperatures, but not necessarily in the face of the wide suite of other stressors that they have to deal with. So we're looking at how these warming temperatures are affecting juvenile health and their parasite loads. And of course, SRC also has a key outreach mission. We take almost 1,000 high school students from South Florida, shark tagging every year, to get them hands-on with both science and marine conservation.
Guys, if I can get 5 scientists to talk about the things that they love in less than 3 minutes, then we can do anything. All right, so we are making up some time this morning because Miami has made nothing easy for us. And so this is going to be a relatively brief panel conversation. Everyone's shaving some time. So rather than going to individual questions, what I'd like to ask you, and this is open to anybody, is that's what we know. Where are the gaps? Where are the questions that we really need to answer next in order to properly manage Biscayne Bay?
All right.
Please, Dr.
I'm
Castaneda.
gonna be the first one. You notice that in my presentation, I focus in the Florida Coastal Everglades, right? The reason that we did that is because we had 24 years of data for mangrove monitoring. And what are the effects of environmental gradients, the effects of sea level rise, climate variability? We don't have a long-term monitoring program in Biscayne Bay. We know that the concentration of mangroves are in the south part of the bay, and there are studies, of course, and I show some of them at the end, but we need a better comprehensive studies that basically assess first, what are the carbon stocks? And all the time we talk about the ecosystem services that mangroves provide, right? And carbon stock sequestration is one of them. We had done that for the Everglades. We need to do that because it's the way that we're gonna estimate what are the cost benefit of these mangroves and the ecosystem services that they provide.
Thank you so much. Please go for it.
All right. Phosphorus pollution is different than nitrogen pollution. In so much of the world, nitrogen pollution causes loss of seagrasses. But the thing about nitrogen is bacteria turn it back into atmospheric nitrogen in the system. There is no bacterial removal of phosphorus that goes on, which means the phosphorus we put in the system is permanently in the system. So the big research gap that I see is how do we ameliorate the phosphorus loading that's already happened within the system so that we can return to a system that's dominated by slower growing. So this is a technological issue, it's a science issue, it's a management issue. We need to be talking across interest groups.
I'm going to ask a follow-up really quick. What options do we have to ameliorate phosphorus?
Well, one is burial. You know, through time, as sea level rises, we're going to accumulate sediments that doesn't have so much phosphorus in it, and that'll eventually cap the phosphorus.
Okay.
There are technologies out there for removal of phosphorus by removal of biomass. You can put rusty particles out and phosphorus sticks to rust and you can remove them. So there are techniques that have worked at small scale and in farm ponds. It's quite different to think about applying those over the scale of this.
What are our natural options?
Well, stop putting it in.
Sure.
And wait a long time
Okay.
for it to be buried,
Okay.
right? Either that or we're gonna have to go harvest biomass for decades to come and take that and turn it into phosphorus fertilizer to be used in Iowa or something, get it out of here, to slowly reduce the phosphorus.
I mean, this makes your work, Dr. Castaneda, so important in terms of restoring wetlands.
Definitely. One example that we have also is the storm treatment areas in the central part of the Everglades. I mean, it's the largest man-made constructed wetlands that we have in the world. 63,000 acres that basically take out the pollution coming from the agricultural areas. So So it's a lot of cleaning that we do in the upper part, but in the lower part, like Biscayne Bay, we have a lot of pollution coming into the bay. So we need to implement these mangroves and general coastal wetlands as a tertiary systems. It's something that has been implemented in Latin America for the shrimp agriculture, and it helps to clean the water and then maintain the health of the ecosystem, the other ecosystem like seagrasses and coral reefs.
Yeah, I think it's really important to look at models in other locations where we have some solutions we can look at. Please, Dr. Cañete.
Yeah, I'm not gonna take too much time. I was gonna say, like, in terms of another, like, emerging contaminants, I mean, especially I mentioned about PFAS. I think there's a lot to still understand about their fate, like how much is partitioned, it can be in the sediments, we have been actually researching, looking at how much it by accumulating in biota, like, marine organisms like oysters, fish, we have been looking at lobsters as well, so most of the recreational fishers. And I was gonna say one of the major challenges is, okay, how can we remediate those contaminants from the bay, right? I think like probably what everybody's asking themselves. So that's something that, I mean, we also have been looking through some solutions, again, underway.
Thank you.
That's it.
Thank you. As far as the research, I think we need to, we have historical data sets that are a gold mine to explore. I think we need to focus on tipping points. Those slow, gradual declines don't really capture the attention of the media, but crashes and demises do. But we need to be proactive and try to identify where the next one mass decline is coming from and develop interventions. Seagrass restoration is not really being considered. It's costly and it's slow process. Algal removal not being considered, but again, we may be approaching the point in time where we, like with coral reefs, need to start thinking about active interventions.
Thank you.
I'm talking against my own interest here as an ecologist, but I do think that there's a big piece of it that's about how we draw all of the connections that need to be drawn between social systems and ecological systems, and how we turn that into management decision-making, where for any, we're talking about mangroves and seagrasses and sharks, right? But we're not necessarily as good at fully illuminating the connections between all of those things and making them feel relevant to people. And I think that people have a hard time drawing the connection between habitats or animals they care about and fertilizing their lawn. So trying to figure out how to kind of make some of those connections more explicit.
Yeah, one of the takeaways for me, for all of you, is that there's something here for everybody to care about. Dr. Cañete, I know, the forever chemicals, people kind of shy away from them because they're scary, but it cannot underline more how much our fates are connected to the ecosystems that we live in. We cannot escape it. All right. I am getting the gaff from downstairs to move things along, but I want to give you guys an opportunity. Lightning. You've got a room full of people with all different backgrounds. You're a scientist. Give me the one bullet point. What do you wish that they knew? Doesn't have to go down the line. Anybody's first.
All right. Think about low nutrient environments like slow growing things. They're the things that they're dominant. We love those slow growing things. The first sign in the Southern Bay that we're losing seagrass is we're changing from slow growing turtle grass to fast growing shoalweed. Okay. That showed up in your data, Diego. So look for not just changes in whether the system is there or not, but there are little changes within the system that can tell us what's going to happen.
Also, we know climate change is happening. Sea level rise, hurricanes, and hurricanes not only they are really destructive, especially for mangroves and seagrasses, but also they have positive effects. And the reasons that mangroves also recover post-disturbance is because the pulsing that these storms have, they deposit mineral nutrients with high contents of phosphorus that basically helps to for the mangroves to recover it and also create plant-soil interactions that contribute to the fast recovery of the wetlands.
Any other very brief thoughts?
Quickly, we're not going anywhere, and we are multiplying. So we need to think about the type of bay that we want to have into the future, which will look very different from what we had historically.
Yeah.
So we need to come to terms of that and act towards preserving what can be preserved and restoring what can be restored.
And along those lines, I want to add that it's not over. It's not even close to over. There's still so much there. And the choices that we make will matter to what happens next.
All right, I think we're going to cut it there.